In this video, I will explain how you can use Thymio as a drawing machine. You have probably noticed that Thymio has a hole in its housing that sits right in the middle between the two wheels. So if you put a pen in this hole, you can draw the trace of the robot's movement on a piece of paper. And if you manage to write a program that lets the robot perform a repeated sequence of movements, you can create beautiful ornaments. Look at the nice examples created by some of my students. We usually used A3 sheets because with A4 you might probably feel a bit limited in size. So what I really like about this activity is that it is a creative task. In other words, it's not just about logical thinking to create a program. Actually, the structure of such a program is not that complex. But besides logical thinking, this activity also requires a lot of geometric imagination. And in addition, it's not possible to create such a beautiful ornament in one go. You have to develop this step by step. To describe it as a strategy, one could call it stepwise refinement. And this is a process that demands a certain amount of perseverance. I can tell you, this activity can be quite painful for some of the very impatient learners, but on the other hand, it can become so exciting for all those who really get into it. To conclude, I can say, if you want to challenge the left and the right hemisphere of the brains of your learners and at the same time foster some valuable social skills, this is definitely an activity you should try. Before I will suggest a program structure, I would like to talk about the geometrical aspects first. It is not the idea that you should explain all this to your learners, but it is useful to have these thoughts in mind to give your learners some support if they need it. This is especially true for younger learners or for learners who have difficulties with their geometric imagination. But sometimes it's also necessary to explain some principles because your learners have used a different system. Let's say a system that offers a move command where you can specify a distance to move an object from point A to B. Usually there is also a command to change the direction, and then you can move your object forward in another direction. You can find these concepts from, for example, in systems like Bbot or in a Scratch programming environment. Now, with Thymio and VPL, the whole thing becomes a bit more dynamic because we will work with speed values in combination with a timer. So, it's always a play with speed and time. And if you think now that this is too difficult for your learners, I can assure you that every child has this knowledge. Just watch children running around. The only problem is that this knowledge is often not conscious. Every child who wants to run from A to B knows that they have to speed up if they want to reach point B a little earlier. So you see, this combination of speed and time is so natural that we don't even think about it. But what if there were an obstacle between point A and B? That's quite simple. We just have to move on a kind of circular line to avoid this obstacle. But how can you succeed in moving your body on a circular line? That is also very simple. You just have to take shorter steps on the inner side of the circle. But how often do we really think about this basic principle of movement? You see how deeply this is implanted in our being. And this is the point why I like working with a small robot like Thymio. This robot is an object that can move on a flat surface much like we humans do. Just imagine how strange it would look like if you saw a child running around on a playground in a pattern that looked like this. If this movement occurred at a constant speed, I would even think of an autistic behavior disorder. I mean, these concepts are interesting too, but I don't understand why so many teachers think that we should start with these artificial concepts first. Just take a walk through the forest and tell me afterwards how many right angles you have discovered during your walk. The main goal cannot be to just teach a programming language. The skills you need to create a program or a software system are the ability to maintain a natural curiosity that allows you to observe patterns, to see connections in creative ways. And the more mature learners become, the more programming elements or mathematical concepts we can give them to be constructive. The desire to learn a programming language must emerge from the desire to describe or express something. And using programming elements to get a little robot to create such a beautiful drawing through movement patterns is definitely such an expressive activity. Now, let's talk about the geometric elements. As humans, we move on two legs, and our robot moves on two wheels. It's not quite the same, but as long as you only have to move on a flat surface, wheels are just as good as legs. So the first point is quite simple. If both wheels move at the same speed, the robot moves on a straight line. When you reduce the speed on one wheel, it moves on a circular line. But where is the center of the circle? If the speed difference is only small, the center of the circle can be quite far away from the robot. But the more you reduce the speed on this wheel, the closer the pivot point gets. And if you reduce the speed to 0, the robot turns exactly around this wheel, which results in a radius that is half the distance between the wheels. And this is always a good orientation point. But what if you wanted a radius smaller than that? Then you have to set the pivot point somewhere between the wheels. Now, look what happens. The right wheel turns slightly backwards. And if I move the pivot point even closer to the center of the robot, the right wheel starts turning faster, but of course still in the opposite direction. If I increase the absolute speed of the right wheel to the same value as on the left side, the pivot point ends up at the center of the robot. So the robot turns on the spot, which means around its hole. As a result, you see that we can draw straight lines and circular lines with any radius we want, from 0 to infinite. Actually, we can consider a straight line as a circle with an infinite radius. But please don't confuse you students too much. To kick this activity off, I usually show my students a simple ornament. And then I ask them to find the geometric elements that compose this ornament. Most often, the answer comes rather quickly. The ornament consists of straight lines and circular arcs. This means that the robot should start by drawing a straight line followed by an arc, and then repeat this sequence for a certain number of times. Now let's call these two elements we have identified phase 0, that starts here, phase 1, and phase 0 again, and phase 1. And then we want to have a start and a stop button to control the drawing process. Here you can use the forward button marked green to start the robot and the round button in the middle that is marked red to stop it. So this is the basic structure of our drawing program. But since we need to use the timer function to trigger the transition from one phase to the next, we need an indicator that tells us in which phase the robot is currently working. A reasonable way to achieve this is to use the LED segments. In WPL3, you can access these LED segments in any way you like. So we can define this LED as phase 0, and we can define the next LED as phase 1. Finally, while the program is being executed, we can visually observe the phase the robot is working on. Drawing a straight line here, and then drawing the arc here, and then back again to the straight line, and so on. And this visual feedback is extremely valuable if we want to add more phases to the program later on. Now it's time to have a look at the program structure. I've prepared a simple program for you with only 2 phases. As soon as I press the start button, the motors will start and you can observe the switching between the 2 phases on the LED ring. You have probably noticed that phase 0 draws the straight line and phase 1 creates the arc. Here you can see the core part of the program. In the first line you see the blue action blocks needed to start phase 0, in which the robot moves straight forward with 2 equal speed values. The timer is set to 1 second to end this phase as soon as it expires, and LED 0 is set to indicate phase 0. In the second line, you can see the action block that sets the motor speed on the right hand side to drive backwards, and the timer is set to 2.5 seconds. LED 1 is set to indicate phase 1. If you now look at the red timer event block in the first line, you see this timer event combined with the condition that LED 1 must be switched on. This means that the action part of this line is only executed if the robot is currently in phase 1. In other words, the timer event marks the end of phase 1 and must therefore initiate phase 0. On the second line, you see that the timer event is combined with the condition of LED 0 switched on. And this is because the actions that start phase 1 must follow as soon as the time for phase 0 expires. The big question now is how to get this system started. If we use the Start button to trigger phase 0, we can copy the first line and replace the timer event with the Start button event. This works fine, but there is one big drawback. We have to maintain two lines with exactly the same action blocks, which means if we have to change something in phase 0, we always have to make sure that both lines are changed in the same way. This is a problem of maintainability. Therefore, I will show you a little trick how to avoid this problem. Take a look at the entire program now. In the second line, you see the start function. My trick is to start the timer with the shortest possible time, which is 0.1 seconds, and at the same time switch on LED 1. As a result, when the timer expires in this condition, phase 0 will start. The short delay between pressing the Start button and the start of the motors is hardly noticeable. Finally, have a look at the first line. This line defines the stop function. The motors are stopped and all LED segments switched off. It is not sufficient to stop the motors. You must clear the LEDs. Otherwise, the expiring timer could start the motors again. Now the program is complete. I suggest that you discuss this program structure with your students before adding more phases to the program. Let's now look at how a program with more than 2 phases can look. I will first show you the program in operation. You can see that the first phase creates a straight line, and the last phase turns the robot on the spot with a radius of 0. And you will see that after 4 iterations, the drawing is already finished. The presented program is based on 6 phases, phase 0 to 5. The green arrows show you how to set the conditions with the LED segments for the timer events. The blue arrow shows that you have to make sure that the first phase starts after the last phase, in our case, phase 5. Also pay attention to the red arrow, which shows that the start function must also set the LED corresponding to the last phase. Now let's examine how the speed and time values are set for the different phases. You can see that there are two straight lines of equal length, one in phase 0 and one in phase 4. There are also two faces with arcs of the same radius and length in phase 1 and 3. The arc in phase 2 rotates counterclockwise with a smaller radius. You can recognize this by the slightly higher speed of the wheel turning backwards. And the last phase turns the robot on the spot through an angle of about 180 degrees. As you've probably already recognized, phases 0 to 4 create a kind of heart shape. And one of the last changes I made to this ornament were in phase 2, because I wanted to make this heart shape a little wider. So I had to shorten the arc in phase 2 by shortening the time of this phase. Finally, I ended up with a heart shape that covers about a quarter of the whole ornament. But this change made the whole drawing slightly smaller, and the straight lines in phase 0 and 4 started to overlap at the center of the drawing. As a result, I had to shorten the two straight lines by reducing the times of those two phases as well. This example shows why it's not recommendable to make two modifications at once. You always have to consider the impact on the whole structure. In addition, this situation shows that my thinking jumps from the observer position, in which I look at the drawing as a whole, to the field position, in which I have to recognize what the robot has to do in order to achieve the desired effect at the position where it reaches phase 2. Now you see how much this activity stimulates my geometric imagination. On my final slide, I would like to show you another example where my students introduced a backward movement. As you can see, the drawing starts with a straight line followed by an arc, and then the robot moves backwards with a fairly large radius in phase 2. The sharp corners in this drawing are not the result of a turning on the spot, as it might seem. They are generated by a backward movement, and the program is based on 3 phases only. Finally, I hope you have received some inspiration that will motivate you to design your own ornaments, or better yet, have your students design their own. When I look at these ornaments, I don't have the feeling I'm looking at a reproducible computer printout. It doesn't have the same kind of accuracy. Rather, I have the impression of a handmade product. But what gives me that feeling? It is probably because there is a subtle process behind that involves many steps to complete these individual works. And no two drawings look exactly the same. Even a tiny change can modify the appearance significantly. There might even be a difference between two robots, because no technical calibration can be absolutely the same. And I noticed that during the video recordings, my students always knew exactly where to place the robot to start the drawing, and they had a clear feeling after how many repetitions the robot should stop. This showed me that they had developed a clear vision of the look of their work of art. And this involvement is exactly what makes this activity so valuable. Thank you very much for watching this video, and have a lot of fun using Thymio as a drawing machine.